Ever wondered if our DNA can hide secrets just like a coded message? Well, believe it or not, it can. Welcome to the fascinating world of DNA steganography, where science meets the art of concealment. In the simplest terms, DNA steganography is the process of encoding data into DNA sequences. It's like using the building blocks of life as a secret storage unit. But we're not talking about a few lines of text. Oh no, this technology has the potential to store mind-boggling amounts of information. Imagine the entire works of Shakespeare, the Mona Lisa, and the theory of relativity, all tucked away within the microscopic structures that make up your DNA. Sounds like science fiction, right? But this is the reality of DNA steganography. This technology leverages the enormous storage capacity of DNA, allowing us to condense an unbelievable amount of information into an incredibly small biological space. Imagine being able to carry an entire library in a single strand of your hair. Curious about how DNA steganography works? Let's dive into the science behind it. DNA steganography is a fascinating intersection of biology and computer science, where digital information is hidden within DNA sequences. Yes, you heard it right. We're using the blueprint of life itself to store data. The process starts with the digital data you want to store. This could be a picture, a document, a song, any form of digital information. This data is represented in binary format, a series of ones and zeros, which is the language computers understand. Now here's where the magic happens. We take this binary data and convert it into a 4-letter code. These 4 letters are the building blocks of DNA: adenine, thymine, guanine, and cytosine, often abbreviated as A, T, G, and C. Each binary digit pair is translated into a specific DNA base. For example, one could map 00 to A, 01 to T, 10 to G, and 11 to C. Once we have our DNA sequence, we're not quite done yet. Up next is the process of DNA synthesis. This is where the digital DNA becomes physical. It involves assembling the DNA bases in the correct order to match our sequence, creating a synthetic strand of DNA. It's a complex process, but thanks to advances in biotechnology, it's becoming more accessible and cost-effective. And there you have it. The digital data is now stored within a strand of DNA. It's incredibly compact and durable. DNA can last for thousands of years if stored properly, far outlasting any hard drive. And a single gram of DNA can store an estimated 1 zettabyte of digital data. That's a 1 followed by 21 zeros. But it's not just about storage. DNA steganography also allows for data to be hidden in plain sight. Unless you know what you're looking for and have the means to sequence and decode the DNA, the information remains concealed. It's like writing a novel, where the alphabet only has 4 letters and the book is a tiny strand of DNA. So next time you look at a strand of hair or a leaf, remember, it could be carrying a secret message or an entire library of information. Now, what could we possibly achieve with DNA steganography? And what hurdles do we face? DNA steganography, it's like a secret handshake in the world of molecular biology. It's an intriguing concept that holds immense potential. One of the most promising applications lies in the field of data storage. DNA can store information in an ultra-compact form that far outstrips traditional digital storage. Imagine, if you will, storing the entire internet's data in a device the size of a sugar cube. That's the potential of DNA data storage. But it's not just about storage. DNA steganography also promises to revolutionize data security. The ability to hide data within the DNA of living organisms could provide an unprecedented level of security. In an era where traditional encryption methods are constantly under threat, DNA steganography could be the next frontier in securing our digital lives. And let's not forget about biological computing. Here, DNA steganography could play a vital role in developing biological systems that can process information, akin to a biological computer. However, as with any emerging technology, DNA steganography is not without its challenges. The biggest of these is the cost. Synthesizing DNA is an expensive process, and while costs are falling, they remain a significant barrier. Then there's the issue of data retrieval. Extracting data from DNA is a complex process and prone to errors. Even a single error during data extraction can render the stored data useless. And finally, there's the question of durability. DNA is a fragile molecule and can degrade over time, potentially leading to data loss. So yes, there are hurdles. But none of them are insurmountable. With advancements in biotechnology and the increasing need for secure and compact data storage, the stage is set for DNA steganography to take a leap forward. DNA steganography may still be in its infancy, but its potential to revolutionize data storage and security is immense.